Hey, I'm going to do these chapter 4, 5 through 13 odds. I accidentally started doing this and realized I hadn't started the recording. So, let me talk you through what I did here in number 5. I made a little picture because I like to do that, and this train is going 60 kilometers per hour, which is the same as 1 kilometer per minute. So, all these times that they give, if it's doing that for 40 minutes, that's 40 kilometers. So there's my 40 kilometers due east, and then 20 kilometers, because it's doing this for 20 minutes. And, notice here that I'm not fussing too much about trying to draw this to scale. This is just a visual to help me get everything set up. They said that the train was going 50 degrees east of north. Now, east of north is an angle measured from vertical, and I like angles to be always measured from horizontal, don't you? So I changed that to 40 degrees here, because then horizontal goes with cosine and vertical goes with sine, all that unit circle stuff. Everything you know about trig, all your intuitions are going to be more solid there, I think. You don't have to do that. You can just put the 50-degree angle here and be careful about finding the legs of your triangle. So then it goes due west for 50 minutes, so that's 50 kilometers there. So average velocity is displacement divided by time, and my displacement here, if you think about this as final minus initial, if I just think of this as the origin, then, and if you're thinking, oh wait, how come you can do that? We could make this any point we wanted to, but it's easiest if we make it the origin. The displacement would be the same regardless of what we call this location, because it's this minus this. All right, so we need to find that displacement, and what I did here is I just set these up as unit vectors. This one was easy because it's just 40i. This is easy, it's just minus 50i. And then this one, I just had to break it up into its components, 15 and 13, by doing some trigonometry. And then I added them up because that's the easiest way to add vectors in component form. And I got this. And then I went through here, and I think I actually made a little, added up a time wrong. I think this is incorrect. So in the answer in the back of the book, instead of having 69, I think they have 21. They might have rounded slightly differently. They have 22, I think, and they have 22 degrees east of north. But that's the same as 69 degrees or 68 degrees north of east, which I prefer. The other one's perfectly correct. And then if you add up all the times, you've got 40 minutes and 20 minutes is an hour and 50 minutes. That's 1.83 hours. And 14 divided by 1.83 is about 7.7 kilometers per hour at that angle there. And double check. Let's see. Yep. That's good. They have 7.6, but they just rounded somewhere a little differently along the way, so that's all good. All right. Number 7. An ion's position vector is initially, I call this R initial, 5i minus 6j plus 2k. Hey, my physics teacher said there wasn't going to be any three-dimensional stuff here. What's up with that? Well, it's all the same. It's fine. Just a little bit of practice here. When we get a little bit deeper into things, we will not be doing three-dimensional stuff, but it's fine here. All the rules are the same. All right, all in meters. I dropped the point zeros on all those just for ease of doing math. In unit vector notation, what is the average velocity during the 10 seconds? Time elapsed here is 10 seconds between those. Okay, so, well, it's delta r over delta t, delta position over delta time. That's how you find average velocity, just like feels like doing slope, right? Final minus initial over t2 minus t1, or t final minus t initial. So I need to do this minus this. So r final minus r initial over change in time, which is 10 seconds. So let's see, this minus that, that's minus 7i. This minus that is 14j. And this minus that is minus 4k, all over 10 seconds. And they want the answer to be in unit vector notation. So my average velocity is negative 0.7i plus 1.4j minus 0.4k meters per second. That's my average velocity. That's all we need to do there. Check answer. Looks good. Number 9, squirrel season out there. They're out there gathering nuts, preparing for the winter. He's moving around on level ground. We got a little map here that shows where the squirrel is at, in particular at these locations A, B, C, and D. And they tell us the times. They're spaced out 5 minutes apart time-wise. And finally, let's see, sorry. Finally at D, blah, blah, blah. Consider the average velocities of the squirrel from point A to each of the other 3 points. And then, of them, what are the magnitude and angle of the one with the least magnitude and the one with the greatest? So I guess we should just find them all, and then we can compare. So, A to B. We want to find comparing average velocities. So from A to B, what is the displacement? Well, you could do, find the actual position at B and subtract the position at A, or you can just look at the vector that points directly from A to B. Those are both going to give you the same thing. That seems unusual to you. You should try both ways real quick and just see that that is true. So from A to B, in unit vector notation, A to B goes 1, 2, 3, 4, 5. All right, 1, 2, 3, 3 blocks over, and each one of those is 5. So the displacement is positive 5 meters in the I direction to get from A to B, and down 1, 2, 3, 4, 5, 6 blocks in the J direction, and that takes that's meters. That takes 5 minutes from A to B. So we can find that we can find this average velocity in unit vector notation if we want to, or we could find the magnitude of this and then divide by that there. Either one of those would be just fine to get what we need. So I have 1i, 5 divided by 5, minus 6j meters per second. And just going to find the magnitude and direction real quick here. So my magnitude is the square root of 37. Which is about 6.1 meters per second. And the direction is the tangent inverse of 6 over 1. Not going to put the negative sign in there. It's about 81 degrees. And that's positive 1 -6, so it's in the fourth quadrant, so that is 81 degrees, I'm going to say below positive x-axis. They didn't say anything about north, south, east, west here, so I'm not going to do that. All right, from A to C, same thing. From A to C, they're happening in 5-minute increments. So from A to C is going to be 10 minutes now. And to get from A to C, don't have to go very far at all. I just have to go 5 meters in the I direction. And, oh, did I mess this up? Is that supposed to be a 25? Why did I write a 5 there? Hold on a second. I might have to go back and fix that. 1, 2. That's 3 blocks over. Where did I get a 5? That should be 15. All right, let's fix that real quick. Shouldn't take long to do. You were probably screaming at the screen there. Sorry about that. So that's going to be the square root of 45 instead. That's 6.7. And then my direction is a tangent inverse of 6 over 3. That's 63 degrees. Sorry about that. All right, easy fix. And then, glad we caught that. So here, 5, and then nothing in the j direction, right? No up and down. So that gives me a half I plus 0j meters per, oh, did I say second here? This is minutes, isn't it? Jeez, McGrath. Mistakes abound. This is meters per minute. So the magnitude, this one is not going to win for biggest. I guess this could be the smallest magnitude. Direction. So if I Pythagorize these, the magnitude of that, since there's no j component, and then the direction is the direction of the positive x-axis. From A to C. All right, that was easy. A to D. Well, this will be easy too. A little bit more math. So from A to D, let's see. In the I direction, I have 1, 2, 3, 4, 5, 6 blocks over. So that's 30I. And then looks like I'm going up, so that'll be positive. I'm going up 1, 2, 3. So it looks like 60 meters. Up. Hope I counted that right. Meters, and this takes 15 minutes because that's from time A to D. And let's see, so it's 2I plus 4J meters per minute. And I think this is going to be in the middle of these in terms of magnitude, so I don't think this is one of the ones we have to report, but let's just do this anyway. Magnitude is, let's see, 16, was square root of 20. About 4.5 meters per minute. That's the average speed if we just ignore the direction, right? Average speed. The direction would be tangent inverse of, oh, it's also tangent inverse of 2. So it's the same, it's 63 degrees, but now we're above positive x-axis. All right, so what do they want us to report here? A, what's the magnitude and angle of the one with the least? So that would be this. So this is A, B, and then what's the magnitude and angle of the one with the greatest? That would be those. Let's just check our answers here. Hopefully we did okay. For, let's see, 9, 7, Centimeters per second. They converted things to centimeters per second. Why on earth would they do that? So I can double check and make sure that ours are okay. They reported the angles as negative 63 here. So what do they have here? They had this as 0.83 centimeters per second, and then they have this one, the greatest, as 0.11 meters per second. So that should be easy. You just divide that 6.7 divided by 60. Oops. 6.7 divided by 60. So that's good. That's the same. I don't know why they did different units than what they gave. So that's correct. That's fine. And this, I'm going to presume that that is correct also. So 0.5. Yep. That's good. I'm perfectly happy with those answers. Not because they're mine, because that's the units that they were giving in the problem. So why would they change it? Weird. All right, number 11. This little section is called average acceleration and instantaneous acceleration. So looking back at my notes here, my 2D motion notes, average acceleration is like the difference in velocities, right? Just like a slope kind of feel. And the instantaneous acceleration is the derivative of velocity. And did we do that in the notes? Ooh, look at that. Maybe we need to add to the notes here that your actual acceleration, which if nobody says anything otherwise, you assume that that's instantaneous, is equal to the derivative of velocity. I guess I just figured your calculus teacher had told you that. So we know that from 1D, and it's the same here. All right, so let's see what we got. The position r of a particle moving in an xy plane is given by this function. So r is equal to, and you notice that each component, like in the I direction, it has its own little function, and in the j direction, it's got its own little function. Right, so we could look at just this, what's happening in the horizontal direction and what's happening in the vertical direction. You can just treat those separately. And this is r is in meters, t is in seconds. And unit vector notation, calculate r, v, and a at time 2. Okay, well, at time 2, I guess I just need to plug 2 in. You know what, before I set that up, I'm going to go ahead and just do my little calculus here so I can have these all stacked up. The velocity would be the derivative of this, so that would be 6t squared minus 5 plus negative 28t cubed j, and the acceleration, the instantaneous acceleration, would be derivative of that. Is that negative 84? All right, so we want to know what is the position at time 2. You can write that like a little function notation. That's perfectly fine. So let's see, can I do that without a calculator? 2 cubed is 8 times 2 is 11 I. And then 2 to the 4th is 16 times 7 is, what is that, 112? 6, I'm not going to take any chances here. 6 minus 7 times 16 minus 106j. And then velocity and acceleration also at time 2. that is going to be 2 squared is 4 times 6 is 24 minus 5 is 19. I minus 2 cubed is 28 times 8. And there you go. Hopefully those are all correct. We'll check in just a second. And then they want to know what's the angle between the positive direction of the x-axis and a line tangent to the particle's path at time 2. Okay, I don't think we talked about this in the notes, so let's think about this for a minute. A line tangent to the particle's path. That's a direction, right? So is it the direction of this, or this? The question is the direction that something is actually traveling in the direction of its position, the direction of its velocity, or the direction of its acceleration? So think about that for a minute. So imagine you have something traveling in an xy plane, 2 dimensions like this, and you're interested in knowing what is the angle of a tangent to its path. So in any location as it goes through its little journey here, the velocity vector is the one that's pointing in the direction that it's going. Now, depending on where the origin is here, let's say the choice of the origin is really arbitrary. So its position, the position vector is the vector that points from the origin to that location. So that's definitely not the direction that it's going in. That points to where it is. The velocity is the one that points in the direction that it's going. And then the acceleration is the one that points in the direction that the velocity is changing. So as this bends around this way, the acceleration would have to be pointing somewhere like in that direction because it's bending the velocity around this way. So the answer to part D, the answer to that question in general, is if you want to know the direction of travel, and that's same as tangent to the path, that is direction of velocity. So to find that answer, we just need a tangent inverse this. So that's tangent inverse of 224 over 19. Oops. 224 over 19. That's about 85 degrees. Now, that's positive, negative. That's fourth quadrant. So that we could either say that that's negative 85 degrees will be what the book's looking for, or you could go all the way around and say that it's 275 degrees. Right? All right, let's check those answers. See how we did. Number 11. So a 6 minus... Oh, why do they have 6 here? What did I... How do they have 6 there? That's not right. And I'll double check that in a second. And then 19 minus 224 and 24 minus 336, negative 85 degrees. Yeah, so we're all good. They have 6 here. I just think that that is a mistake on their part. Isn't it? We didn't do anything wrong there. Yeah. Oh, did I not subtract the... No, that's right. Isn't it? 2 cubed is 8 times 2 Yeah, I don't know what they were doing. So I'm sticking with this. All right. 13. The last one. Particle moves so that its position in meters as a function of time is this. Write an expression for its velocity and accelerations as functions of time. So let's see. Particle r is equal to I. Just the I by itself, that's like 1I. That is a weird looking I. Let's try that again. That's better. Plus 4t squared j plus t k. And they want expressions for velocity and acceleration as functions of time. So part A, what's the velocity? It's just the derivative of this. The derivative of 1 is 0, so there's no component there. You can leave that off, or you can write 0. Here, that's going to be 8t. And then here, the derivative of t is 1. So I could write a 1 there, or just k. Either way is fine. And then the acceleration is going to be, that's 0 again. Here, it would be 8j, and now that's 0. Right? And that's it.